I like your background.
Jordan? And there's a laser pointer up there if you need it.
Alright, my name is Jordan Rogers, and I'd like to introduce you to the Hoover function. It's a function typically used in shell structures. It has a stress function, which we use to calculate membrane forces in shells. The middle surface, which we're going to talk about in a minute, it must be defined. It's typically as a function of z, which equaling f of x, y. Slight definition of middle surface is it passes between the two faces. In other words, you have a shell structure, you're looking at the midpoint between that surface. So however deep it is, that's what your mid surface is. If you have an irregular mid surface, such as let's say your client wants an undulating surface and it really isn't a function that describes it, that's where your numerical methods can be employed to find those stresses. It can also be used, if you just want to, it can be used to evaluate a function that does have a continuous curve to it. And the components are defined by a unit area, and the x, y, and z. The x, y, and z is typically just a expression of a unit per area, so it's not referring to the coordinates. In this example here, it's referring to a unit of area. This is an elemental picture of the shell we're talking about, and it's just this right here. This is just the area that it would cover. What I have here. But yes, as I said, the x, y, and z is just a unit of area. We have highlighted these to show you the main forces in the x and your y here. So you have this little arrow there, which is the y component here, no x component, sorry. And then this right here is expressing your y component. So it's you can see it's a partial differential equation because there is, as you go from one point to the other, you have two variables changing simultaneously. So you have to use a partial differential equation to solve this. It says here the static equilibrium of the elements subjected to the magnitudes is expressed by these two equations, and we're going to further integrate these equations into the Hoover function to come up with an equation that could evaluate different types of shells. So this right here would be saying your sum of forces equals 0. So we're saying, so we're saying right here is our x's, this is our y's, this is our z's, and they're going to equal 0. So this is just expressing this in that picture there again. So defining the static equation is just a little more expanding on it. We have our x, y's here, and y's, and those are right here. So we're going to substitute those a little bit into the entire equation just to be able to simplify things, make it a little more possibly comprehensible. And this is an expression of the tangent of theta and the tangent of, I think that's delta. So here, it's getting a little wild, but hang on. This is our x, this is our y, this is our z. And those equations we just saw, we're going to expand on this. So we have this, say that we have this times that, to give us that times that, plus we're going to have it twice, that's where the 2 is coming from here. We have that, and this is going to give us our 2. That's our y's right here. And then the x and the y's is just there because this is the x and that is the y. So hope you can follow that a little bit, but that's what we're going to work with here. And then it's going to turn into having to express what is the middle surfaces we were talking about earlier. Middle surface is something that has to have, when you're taking an integral, you have to start at one point and end at another. Where your starting point is going to stay fixed, which is this x naught and your y naught. Those both are going to stay fixed, and you're going to go to however the span of your shell is, I guess you could say. So we're going to use that. your governing stress equations. And this is just a little more derivation here, but it finally ends up, that's what we're trying to get to. This is going to be your load at the, it gets at the point that you're evaluating, and this is everything else. But all this is going to simplify a bit more. It's a little hairy, but it's really not that complicated once I show you the partials we start taking. This is just an example of a shell. This is something we actually saw in our class analysis too. This is, we're going to evaluate this shell right here, and we're going to combine it to actually form a shell. And it's really, this right here of itself is not particularly a shell until it has those four elements combined together. This is where I was saying it simplifies in this example. All these terms here we were looking at earlier, they all go to zero. The reason they go to zero is because there is, in this example, there's no horizontal forces, there's only vertical force. So you end up with just this equaling z. And then from these partials here, which if you were to go back and look at this, you'll see how they simplified these equations here. But you end up with your z force just equaling zc over 2. And it's really quite simple. And so if from our equations, I want you to recall that we've given numerical operators, which you can overlay typically along a diagonal, which for this example, it's because there is no horizontal forces. As one of our previous presentations talked about stresses being normal along the diagonal of your matrix. So this operator here would be laid on the diagonal of the matrix, and that's where you'd be able to analyze, say, a structure that didn't have a function that you knew. So enough theory. Talk a little bit about some applications. There is just this, which is, it'd be a roof structure, could be a building, I guess, which is just an interesting form, I thought. But what I really found interesting is I was researching further into how shells are used, how they've been used in the past, and I saw this and I was like, what is this? And I realized after reading it was talking about using shells as a foundation element. And it was, I've never taken a soils class, but from what I read, it's basically the idea behind it is if you have say this tile here, it's like 2x2 area, there's only 2 square feet there, but if you tilt it up sideways, you're going to get a greater surface area. So when you take this shell structure here, if you're in an area where you have poor soil conditions, or say the unit of area is highly expensive, so you want to minimize how much area you're purchasing, you can use an idea like this, or even this structure, to maximize your use in your foundation element, I guess you could say. So I thought that was quite interesting, seeing that. Other uses could possibly be, architecturally, could be a wall. This here is a hyperbolic function that we just looked at. It's just formed slightly differently. And this picture here I found, it seems to be at least a little portion of it. I don't believe this could completely be thought of as a shell, but it does have similarities to the shells that we're looking at. This is just another type of shell, elliptic paraboloid. Just more examples of what the Bucher function can analyze. In this example here, I didn't go into quite a lot of detail into studying it, but I do believe there is, because just the orientation of where the function is here being described does have horizontal and vertical forces. So it would be a little more involved, but it's just involving 3 more equations. This is just one more. This is a colloidal surface, which is basically a surface where you have a flat element and you just extrude elements to form a shell. So that's another example of what the function could analyze. Thank you for your time.
I have a question.
Yeah.
Is a dome a shell? What's the difference?
A shell is something that has to have
Is that 4 corners or what?
no, it's not necessarily the corners. It's just you have to be able to have it, I don't know how to explain it. You just have to have a touching in a way that there is no, like that wall we saw that was arching out, it would have moments within, when that's coming down, it doesn't have another force resisting it. It's kind of like a noidal thing. You take that, you can hold that growth there. This is a hyperbolic function, and so within that string, there is an equilibrium. Whereas if you just were to try to keep that curve and not have it touching on one side, there wouldn't be an equilibrium. That's the best explanation I can give.
Thank you.